Hey everyone, welcome back to my daily coding series. This is episode 91. Yesterday I did target sum, which is 2D dynamic programming, and I'm going to get back to more of those, but today I'm going to do a graph problem, which still isn't going to be easy, but those dynamic programming questions are really tough, so I wanted to not do one today. Okay, so I've never seen this problem before. It's called min cost to connect points. So we're given a 2D array where every element in the array contains x of I and y of I. And that's a point. Okay, so and we want to return the minimum cost to connect all points together such that there exists exactly one path between each pair of points. And the Manhattan distance is basically just like what is it? It's the difference in x plus the difference of y. Okay. So we're given these points. All right, so I understand the problem. We're basically given these points, and we have to figure out the minimum distance to connect all of them. Okay, so a brute force approach to this problem would be to connect them in every combination and then take the lowest cost or the lowest distance. I think we could probably get around that. Right, so I wonder if there's some like greedy heuristic we can use where we can just connect. Yeah, because for instance here, like this would also be a distance of 2. So is there multiple ways to do it? Yeah, because you could also, instead of this line right here between 4, 2 and 3, 3, you could have a line between 4, 2 and 2, 2, and that would be the same, as well as you could have a line here instead of here. Or instead of this line, you could have it, or maybe not. Or no, I think it would be the same. Because here it's, if we're defining it as the change in x plus the change in y, this is 1, 1, this is 2, 0, so it would actually be the same. So there's many different combinations, but we only have to return the cost itself. Okay, so I mean, could we just connect every point with its closest neighbor? Well, we have to make sure every point gets connected. So, okay. So I'm just going to see what happens if we try to connect every point with its closest neighbor. So with this one, we would calculate the distance from this to all of the points, and we would find that 2, 2 is the closest, so we'd connect 0, 0 to 2, 2. Now, 2, 2. Okay, so this, if we did it again, it would be any of these. But also to imagine if this was somehow the closest. We already did a connection there, so we don't want to reconnect again. Like if we had something, it's hard to illustrate this without drawing. But let's say we had 0, 0, 1, 1, and then we had like 99, 99. So the correct thing would be to do from 0, 0 to 1, 1, and then 1, 1 to 99, 99. But with this method, you'd say 0, 0, search through all of them, connect with 1, 1, and then for 1, 1, you would search through all of them and connect with 9, 9. Or sorry, you'd say that 0 is actually the closest, but we don't want that. So maybe we can only search for points to the right. Okay, so 0, 0, or maybe not points to the right, but we have to order the points maybe by how close they are and pick the closest one that we're not already connected to. Okay, so 0, 0 connects to 2, 2, and now 2, 2 can connect to any of these that it's not connected to. So I guess we'll just connect with the first one. So now we have an edge here and an edge here. And now 3, 3 is connected to these two already. That's not true. So 3, 3 is not connected to 0, 0, but there already exists a path to them. I wonder if we're trying to make like clusters or something like that. Okay, and then so for 3, 3, so these two are already a part of everything. So maybe we do just go like left to right. Well, we need to know if it's like an island or not. Okay. Because what if, for instance, 0, 0 connected to this one over here? Then now we know both of these are... Maybe we should do it in a sort of depth first way. So instead of going from just left to right, we just like go to the closest point and then the closest point to that point and then the closest point to that point, etc. But we do need to know, like, so what if two are equidistant away, but one of them ends up being like the wrong choice? Is that possible? Yeah, it is. So if... So I'm trying to imagine like, okay, so if we went here, so let's say we were at this point in our depth first search that I was talking about, and we identify the closest point is this one, so we connect it. But really what we should have done is like there's a path over here, and then later on it's like really close to this one. So what example would that look like with numbers? So let's say we have something that's like... Well, if that's the closest one... Well, if it's the closest one, then it would still be less distance than like going around. I don't know, maybe I could assume for now that you just go to the closest one. Is that... Basically, I need to validate if that assumption is true. So validate if I'll just say always connecting closest point solves the problem. So in this one it does, and that's all we have. And can we have duplicate points? I guess we could, but the cost would just be 0, so it wouldn't really matter if we had duplicate points. Alright, so I'm just kind of like putting down numbers and seeing if we can do the depth first. Alright, So you start with any random node. So we'll start with 2, 5. And then we would calculate the distance for all of these, I guess. And then take the minimum. So in that case, that would be 2, 4. So now we would get minimum distance from 2, 4. And then we also say in our graph that if we were to have a graph, we would say that 2, 5 is connected to 2, 4, and 2, 4 is connected to 2, 5. So then we would look from this one, we would get the minimum from all of them. So yeah, I'm wondering how this would go. I mean, we could put it in a heap maybe. So every iteration, we just add all of these to a heap. We extract from the heap, see if it's in our already existing connections, which it is. So then we extract the next distance from the heap, which would be so all right, let's see. The distance from this one is 1 plus 3, 4. The distance from this one is 3 plus 2, 5. All right, so the next distance would be 1, 1. So we're going to add that connection. And by the way, so the cost here, we'll just keep track of the cost. So at this point it was 1, and now it's 1 plus 1 plus 3, so 4. All right, so we've done that connection, and now from 1, 1, we're going to look at the closest thing. So we'll put all of them in a heap, I guess. So I don't know. I don't know if that's the best way to do it, or if there's a way. Okay, so this is kind of interesting. So do you have to always ask the question, like, can I reach? Or maybe we could just do like a visited set. And or we can use this, and we know that. So maybe we can just do like a linear search, and then instead of adding everything to the heap, we can only add, or maybe we don't even need a heap. We just we have like a min. So we initialize it as like infinity, and then check, okay, is this one, did we already visit this one? If it's yes, then we skip it. Did we already visit ourselves? Yes. Did we already visit this one? No. So we'll calculate the distance, which is 4 plus 5, 9. So this updates the minimum because 9 is less than infinity. We visit this one. Yes, it's in our graph. And then 9, 8 is not in our graph, so we'll calculate the distance, which is 8 plus 7, which is greater than 9, so we don't update it. So, and then here we would also just store what the point was, which was 5, 6. So now, okay, we'll make a connection from 1, 1 to 5, 6. And we'll add 5, 6 to 1, 1. All right, and that cost is now plus 9. And then we'll repeat the same thing from 5, 6. So this is visited, this is visited, this is visited, this is visited, this is not, and remember, so this is infinity. And this is not, so we'll add it to the graph. We'll add it to the graph. So we'd see that this is infinity, so the distance. So okay, so this is how you do it if the connecting point always solves the problem. And I can't think of a reason why it wouldn't, at least right now. So I'm going to assume that it's true. So then, all right, so we'd have 5, 6 goes to 9, 8. And what's the cost there? So it's 4 plus 2, which is 8. That's interesting. Well, from 1, 1, yeah, well, I think I kind of like it because if you connect, so when 2, 4 connected to 1, 1, that's also, because it was the shortest one from 2, 4, that doesn't mean that 2, 4 is the closest to 1, 1. In this case it is, but if we had like 1, 2, so I wonder if we should optimize for just like doing the shortest paths that exist. And I think that might be like an algorithm, like Prim's algorithm, or there's another one where you basically, maybe what you do is just find the shortest distances and then go from there. Because in this case, we probably would want to start at 1, 1 to 1, 2 and then go to 2, 1 to 2, 4. Whereas if we just start from 2, 5, then we'll go to 2, 4, then we'll go to 1, 2, then we'll go to 1, 1. And then 1, 1, we'll have to make a huge gap to 5, 6. Whereas 1, 1 shouldn't have to do that. So I wonder if we should find just like the minimum. Maybe we could find the cost between every point. So that would be n squared. So we find the cost between this and all of these. And now this and all of these and this and all of these. So, and we put those all into a heap, and then we just I guess would just like pop them off as long as, or no, we should do the minimum distance between unvisited points. All right, let's pivot. So I think this is false. I'm gonna claim that this is false. So switch to always connecting the shortest edge. So this was, we picked a random point and then just kept always recursively picking the closest. But now we're going to connect the shortest edge of unvisited nodes. All right. And let's keep it like this. So what we would do is, probably what I would do is for each point, we'd have a graph. Or not really a graph, but a dictionary, I guess. So we'd have like an array of dictionaries. And it would be 0 indexed. And then I'm thinking each one of these would just hold the, or maybe that's stupid. Maybe that's probably stupid. Maybe we could just have like a heap. All right. So we'll start with 2, 5, and then we'll just add. So in the heap, we'll have a cost and then the points. Or maybe we could just do like X, Y, and cost, or let's say 0.1, 0.2, and cost. But let's do cost first because we want it to be sorted by cost. So so we have 2, 5 to 1, 1. So in our heap, that cost is 1 plus 4, 5. and that's the point 2, 5, and 1, 1. I'm just going to make the heap like this. So that is good data, right? So we do that for all of them. So I don't know if I really should. That's going to take a long time. Maybe I could make a simple example. Get rid of these. Let's put 1, 2 here. All right, and now it would be 5. So 2, 5 to 5, 6, and then 2, 5 to 1, 2, and then 2, 5 from, oh, that's it. So next would be 1, 1, and then, so we'll do, 4, and then 3, and then 2, and then 1. So it would be 1, 1. Actually, it's more like 3 plus 2 plus 1. So it would be 1, 1 to 5, 6. So it's not that bad, actually. And then it's 1, 1 to 1, 2. And then it's 5, 6 to 1, 2. Right, so we should have, if we're doing 3 plus 2 plus 1, that would be 6. So we have 6, all right. And then that formula would just be n minus 1 times n divided by 2, I think. And this is from the Gauss n plus 1 divided by 2. If you're summing up from numbers 1 to n. Okay. So so the cost here is 5. This cost is 3 plus 1, 4. I don't need all these parentheses, I don't think. Just have to think of it as one element. So I don't need these. All right, this one, it's 1 plus 3, which is 4. This one is 4 plus 5, which is 9. This one is 0 plus 1, which is 1. And this one is 4 plus 4, which is 8. All right, so now this is our data that we have. This is basically all of the edges in the graph. So what we're going to do is have these in a heap, and we'll just extract, and then we also need a visited set, so which is empty. So we'll extract the minimum, which is this, and then we'll just have like cost. So we'll extract the minimum, which is this point, this edge from 1, 1 to 1, 2. So the cost of that is 1. So I'll just like put that over there, symbolize that we are done with it. I'll just increment it like that, indent it. And now we add both of these in visited. So we've 1, 1 is in there and 1, 2 is in there. So we don't, what that means is like we don't want any edge that has these. Okay, so the next minimum is the next minimum. So I'm wondering if this is going to work, but let's just play it out for now. Maybe change visited set. Okay, so the next minimum is 4. So 2, 5, and 5, 6. So we check, are either of these in visited? The answer is no. So we're going to add that, and then we're going to add 2, 5, and 5, 6. The next one is this. So we'll check, are either one of these invisited? The answer is yes. So we would just not do it, I guess. Although maybe we would want to, but let's just say not for now. So then 1, 1 to 1, 2, and 2, 5 to 5, 6. I think we would want this one. Or sorry, this one. But okay, so 5, we check this. Alright, this already has stuff invisited. Next is 8. This has stuff invisited. And this is 9. This has stuff invisited. So, yeah, so we have to do edges that are already invisited because this is not the full. We didn't connect all points. We connected 1, 1 with 1, 2, and 5, 6 with 2, 5, but we need one more connection. So I think so how do we know? So what's our stop condition? Because we do need, once we have this one, then then we'll be good. Maybe it's you pick out 3 edges. So you pick out like half the edges plus 1, I'm thinking. So stop after you choose half the total number of edges plus 1. And my reasoning is, so if we pick half the total number of edges, then that means, so this works with even numbers. If we pick half of the total number of edges, then that means all of them are connected. Like, or not all of them are connected. So that means that there will be half the number of edges. Like every node will connect to another node separately, but none of them are. Oh, maybe this isn't how it works. All right. So let's say we have A, B, C, D, E, F, G. So let's say my algorithm says that A needs to go to B, C needs to go to D, E needs to go to F, and let's say H for now. So this is helping me answer when is the stop condition. And then G goes to H. So how many do we need from here? So we need, so in the case of 8 nodes, 8 points, we would need the first 4 to connect all the points, and then we would need to connect the groups together. So we would need 2 more. We need to connect like this one to any of them, and then so let's say AB connects with CD. Well, we would actually need 3 more, and then let's say these 2 connect, and then we would need to connect them. So it honestly looks like that, like where it gets halved every time. So I don't know if there's like a good way to. Alternatively, we could just keep adding the minimum cost edges until, like, and we could just DFS every time. And see if all the points are in the traversal, but I feel like there's a better way to do it. In this case, we added 4 plus 2 plus 1. You can think of it like you're kind of like, I don't want to use the word partitioning, but you're dividing the number of points. So all right, so let's think of groups. So let's say that every point starts as a group. Every time you add an edge, you are like having the number of, well, when you add 4 edges, you have the number of groups. When you add so that comes out, so this just comes out to be 7 in the case of 8. Is it just like the number of points minus 1? Let's imagine, so A through H is 7. 1, 2, 3, 4, 5, 6, 7. Let's say that it went to I, J, K, L, M, O. So A through O. So then you'd have, sorry about the kind of verboseness of doing this, but I to J. No, we don't want I to J. We want J to K. Wait, did I mess it up? Yeah, I did. We want I to J, K to L, and M to O. So in this case, how many are there? This is 10, 11, 12, 13, 14. So we would want 7 connections. So now we have 7. So we'd want to connect, let's say, this, this, this. So we'd have like, these are connected now, these are connected now, these are connected now. So that would be 3 more. And then we need to connect these 4 groups. So 1, 2, 3. No. Wait, am I crazy? So we connected B with C, so we connected all of them, that's 7. And then B with C, F with G, J with K, so that's 3. Now do we have to do that again? Now we would need, so now we connected, yeah, so now they're in these groups. So now we would have to do D with E, H with I, and L with M, which would be 3 again. And that would be it. So I think it's just the number of nodes minus 1. Is what it looks like. And let me just try one without. That's odd. So if we do A to M. Sorry, I just want to make sure before I start coding it. Yeah, in a real interview here, I'd probably just assume that it's minus 1, but just because I'm practicing. Just want to see. Okay. So in this case, we would do 1 plus 2 plus 3 plus 4 plus 5 plus 6. What would our algorithm do in this case? So I guess it would do, so on the first round, in the way that I'm consolidating it, it would do 6. And then it would connect B with C, F with G, J with K. So that would be 3. And then we would do D with E, H with I, L with M. Which would be 12. Alright, so I'm going to assume now from this, basically just doing it out and looking at the pattern, that the stop condition, stop after you connect node minus 1 edges. Number of nodes minus 1. So in this case, we have 4 and we stopped after 3 connections. Alright. Alright, so I'm gonna, so in summary, so I think I'm ready to start coding it now. So we're basically going to put all edges into a heap, which takes basically n squared, but this formula right here. And then pop from heap n minus 1 times and keep track of cost. And if if the answer we actually wanted to return the graph itself, I would keep track of this. But since we don't really need to do that, I think we would just have a visited set. We don't really need the graph. We can just have the cost. All right. Okay, so it would be, so now like the pseudocode of it, so for, let's say I, all right, I'll start coding it. So I is 0 while I less than length of points. And then inside of this, we want to say at every step when j goes to the end, we want to set j equal to I plus 1. So maybe we could just say I plus 1 to length of points. Just get rid of all the pointers. And let me just start with this and see if that's what I'm looking for. All right. So 0, 1, 0, 2, 0, 3, 0, 4. 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. Okay, perfect. So now let's have a heap. So just import heap q, and then we'll have heap q dot let's call it min heap. Okay, so for every point we're going to add it to the heap. So this part will basically construct heap where we have this. So we'll say so first we should calculate the cost. The cost is so we just have to do the arithmetic here. So points of I, not the arithmetic, but just like the put it out like this. All right, so now that we have these, we'll define the cost as the absolute value in P1 0 minus P2 0 plus the absolute value of P1 1 minus P2 1. All right. Let me just compare that against the formula they gave us. So the two the difference in x's and the difference in y's. It's absolute value. Okay. So now we want to add, so min heap dot heap push. We're going to add the tuple cost P1, P2 to, I think it's actually heap q dot heap push, min heap, and then the tuple. So this should build the heap. So let's verify that. All right, so we should expect that there is, so in this case there's 5, so we should expect that there's 10 using this formula up here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, good. So, and it looks good. So we're going to now we are going to, and what is n? N is the length of points. And this is our stop condition, basically. So we're just going to have a for loop that has, because it's always going to be the number of nodes minus 1. So that's what this is here. So what are we going to do? So we also need a total cost, and then we also need a visited set. So we're going to pop from the heap. Okay, wait. So for this one, the minimum distance, I don't know if what we have to do with the visited stuff yet. So the minimum distance it finds is from 2, 2 to 2, 4. So we connect 2, 2 to 2, 4. Okay, so we connect it here, which is fine. Then it's 3, 3 to 2, 4. So we connect that, 3, 3 to 2, 4. So that's fine. So right now it looks like this. Then it's 2, 2 to 3, 3. So that we don't want. We don't want that. So is it if both the nodes are invisited already? So let's pop it from the heap. I think if both nodes are already visited, then we don't want to make it, obviously. I'll just assume, so don't make the edge if both nodes are already visited. I wonder if it's unideal if like one of the nodes is already visited. I know we have to do that eventually, but should we at least... So in this case, we do 2, 4, 3, 3 to 2, 4. We'd skip this one. Now it would be 3, 3 to 4, 2. So 3, 3 to 4, 2. So right now we have bing, bang, bang. And now it would be, I can't see what that says because it's copy button. Cost of 4 from something to 4, 2. So 2, 2, 4 to 4, 2, I think. And we'd skip that because both of them are already visited. And then it would be a cost of 6. Oh, well, this doesn't look sorted, actually. All right, so I'm going to go under this assumption for now. So what we'll do is if... So we have to make sure that they're not both invisited. So if... so let's pop from the heap. Okay, so if P1 invisited and P2 invisited, then we want to get out of there. Otherwise, we want to cost, let's say total cost plus equals cost, and then visited dot add P1. Okay. Min heap is a list. Oh. Heap q dot heap pop. Sorry, I forget how they do it sometimes. All right. P1. Oh, it's a list. I want them to be tuples. All right, so here we added connection 2.2 to 2.4, 2.2 to 3.3, and 2.2 to 4.2. That's fine, but then we exit out. What about 0.0 to 2.4? It's not printing, but it seems to be adding. Oh, I didn't output anything. Let me print the final costs. Okay, so it seems to be stopping early. Whoops. 42, 46. Okay, so print. P1 and P2 and visited. I want to make sure it's not 3.3 to 2.4. So why is... Oh, I see. These shouldn't count towards our end condition. Yeah, so we can just make it a while loop. So only if we get to here will we add 1 to I. Otherwise, and this could be an infinite loop, but I don't think it will be based on the calculations that we had. Okay. Let's see if this works at all. Alright, so in this case, when I pop from the heap, there is nothing left in there. Alright, let me print what the heap is and see if that looks appropriate. I should have used it as a test case. So we should expect 3 times 4, so minus divided by 2, so 6. So 1, 2, 3, 4, 5, 6, okay. 722. Alright. So we connect this one. Let me put these. Okay, so we add 17.8 and 17.5 with a cost of 7. Then we add this with a cost of 22. And then the rest are just invisited, huh? So yeah, all of them are invisited. Yeah, okay. So this is a problem. It's like, I mean, maybe there's a math trick for it, but basically it's like, how do we know if an edge is good or not? Uh, like, how do we know if we shouldn't add something that's been visited? Because here, what I would think is, okay, so all of the points are unvisited now. So because all of the points are visited, then do we have to reset visited? Yeah, I think it may have been smart to connect to the shortest ones that aren't in visited. Yeah. I'm gonna leave it here for now. I think. I'm pretty sure this is like just a pretty well-known graph algorithm, so I'll research that a little bit more. But it'll definitely make a lot of sense now that I've spent all this time thinking about it. And that's good. Is like you don't always have to get it. Sometimes just like spending time thinking about it will. Now when I look at the solution, I'll remember it way more because I spent all this time thinking about it. Um, Anyway, thanks for watching. That was day 91. I'll see you guys tomorrow for day 92.